Hey there, Calc 3 folks. I'm back with another quick little video over, again, looking at some more application of the double integral, where we are going to, in this case, consider using the double integral to help us find the actual physical volume between two surfaces in three-dimensional space. All right, and as we had noted that actually when we calculate the double integral over a region R for a function f, what it yields for us is what we think of as a net volume of space. That net volume being positive in the positive direction, negative in the negative direction, right? And perhaps canceling at times with each other, in the end yielding what we think of as a net volume of space, right? This understanding about net volume can be used to actually then develop a method for calculating what we think of as the physical volume of space trapped between two surfaces, right? By physical volume, I mean a volume that is described strictly in the positive context, right? It's the amount of space that is taken up between these two surfaces over this region of R here. All right, and the way that this is presented, folks, is by theorem. If I bring that theorem into view, right, it does start by assuming that we have these two surfaces in three dimensions, where one of the surfaces we call M and the other we refer to as N, where what's unique about these two surfaces is that N is always less than or equal to M over all of the values of x and y, here found in this region of R. All right? If it's the case that n is less than or equal to m over all these values of x, y that happen to exist in this region of R, then the volume, the actual physical volume of space trapped between these two surfaces over region R, is described by this calculation here, this double integral calculation, where what we can see is we are forming the double integral over R with respect to the area parameter. All right? How this is understood, folks, depends upon our defined region for R, whereas our integrand here is made up of the difference between the descriptions of our two surfaces. It is given by surface M minus surface N, right? Where M is bigger than or equal to the value of N for all these values of X and Y in region R. All right? This is the way we have of calculating using a double integral to calculate physical volume trapped between these two surfaces. All right, if we look at a quick example, well, first of all, let's look at an illustration of what I am taking note here. I did put together this generic illustration here of this calculation. All right, what we are calculating with this volume calculation, this double integral, is this volume of space found here, right? The volume of space that we've illustrated in this illustration trapped between what we see up here is our surface of M, and what we see down here is our surface N, where we're interested in finding the volume of space trapped between surface M and surface N over this region R that exists down here in two dimensions in the XY coordinate plane. Right? And that might be described using some specific set of values. Now, I did illustrate this as a rectangular region in this illustration. That is just to keep the illustration in a simple context. But region R here can actually be any defined region. All right? Both rectangular and or a generic in its description. And what we may even see at times are going to be polar descriptions of R. All right? So, if we looked at a quick example then, we might consider the volume trapped between these two surfaces, the surface given by 2 plus x plus y, and the surface given by simply z equals 1. Right? Where we are going to be interested here simply in octant 1 of three-dimensional space, where x is bounded between the values of 0 and 2, and y happens to be bounded between the values of 0 and the line x plus 3. All right? What we could note then is that over this regional description of space, right? I should be careful here. We're defining our region here in quadrant 1, right? The region is going to form over quadrant 1 of space in 2 dimensions. What we can note over that quadrant is that 2 plus x plus y will always be bigger than 1. If x is always a number between 0 and 2, and y is a value between 0 and x plus 3, meaning y, if x is between 0 and 2, y will be somewhere between 0 and 5 in value, right? Dependent upon what x is in value, right? What we can note is that 2 plus that x value plus that y value will always be greater than this value of 1. 2 plus any positive values are certainly going to be greater than or equal to this value of 1. So if we consider setting up the double integral over this region, right, to calculate this physical volume trapped between these surfaces, we do note that over this region R, quantity 2 plus x plus y is greater than or equal to 1, and our volume calculation would be given as this, right? So the volume trapped between our surfaces, would be given by this double integral calculation. An integration that happens on the outside with respect to x from these values of 0 to 2, and happens on the inside with respect to y across these functional values of x from 0 to x plus 3. Where inside this integral, we are going to take the difference of our two functions m, which is given by 2 plus x plus y, m being the bigger of the two outputs, minus this function for n, right? N just being the surface z equals 1, right? N being smaller than our value for m, right? Now, starting in our integrand, if we simplify that integrand, this is really just 2 plus x plus y minus 1, which is 1 plus x plus y. Where I am going to consider integrating that from 0 to x plus 3, right, with respect to y. So this would bring about an antiderivative of y for 1, x times y for x, and 1/2 y squared for just the value of y. Where we're going to want to integrate those across the bounds from 0 to x plus 3, right? So here you can see our antiderivative given by y plus xy plus 1/2 y squared. And we now consider evaluating it across these bounds. Certainly at values of y equal to 0, everything zeroes away, so we really are only interested in evaluating it at a y value equal to x plus 3, where if I make this yx plus 3, I make this yx plus 3, and if I make this yx plus 3, expanding that result will yield this quadratic function in terms of x. Where to finish my integration, I am going to integrate this quadratic with respect to x. The 15/2 will become 15/2 x. The 7x will become 7/2 x squared. And the 3/2 x squared will become 3/4 x. Or sorry, 3/6 x cubed, which does simplify into 3/6 becomes 1/2 x cubed. So if I bring that into picture, we can see this antiderivative, where we're going to want to now evaluate it across those bounds. And certainly at a bound of 0, we can see all of this will zero away. But if I make x equal to 2, this will become 15. This will become 14. And this will become 4 in value. So 15 plus 14 plus 4 add up to the result of 33. And the physical volume trapped between these two surfaces is 33 units cubed. All right, folks? So that is another quick description of some application for double integrals that involves, the case for just calculating volume between two surfaces in R sub 3. All right. In this calculation, you are going to have your defined value for R, which could occur over any description of region in two-dimensional space, right? Where inside your integrand, over which you're going to calculate that double integral with respect to R, you are going to form the difference between your two surfaces, surface M minus surface N, right? The tricky part in this calculation often involves determining which surface is going to play the role of M and which surface is going to play the role of N, right? Swapping the role of these two surfaces in the calculation will actually produce the opposite result for physical area calculation. So one thing you might notice is if you go about calculating this and you get a negative value, right, you might consider that you may have your two surfaces mixed up in respect to their order. Now, the other thing you do have to pay attention to is that M and N do not change roles over this region R. That is where producing some graphical illustrations of surfaces M and N, as well as understanding where they're occurring at over R, may be useful, folks. Right? If you notice back down here in our descriptions of M and N, I made it pretty quick to see that 2 plus x plus y was greater than or equal to 1. But what we do want to recall is that this is a surface, right, known as a plane in three-dimensional space that is crossing through the z-axis at 2 and over the first quadrant in two-dimensional space, x plus y is always going to be greater than 0. So x plus y added to 2 will always be bigger than or equal to 2 over this region R in space. Whereas z equal to 1, that is also a plane in space, but that's a very simple plane in space. That's the simple plane strictly passing through the z-axis at z equal to 1 that really illustrates no slope or change in rate of change in z with respect to any change in x or y, right? It's what we might think of as a flat level plane in space, a lot like what I have up here in my illustration, crossing through my z-axis at 1, right? So it will always equal 1, whereas this will always be 2 or greater over this region of R, which allows me to draw this result. All right, folks. That's one other quick video here with respect to a little application on double integration. This concept actually appears in section 16.2, so I pointed out there. And there is one more video that I want to bring back here and present to you that deals with looking at some double integral application where we can actually use double integrals to calculate the area of R. And if you haven't seen that, if you haven't noticed that you have an interesting result there, folks. And we will come back to that in the next video. So I hope you're doing well. I hope you're hanging in there. And I'll be back there, be back shortly with one more video here looking at some application. See y'all then.